Hello everyone and welcome to our video. We are under pressure and I am Shumail Al-Kandari.
I'm Shabib Al-Azimi.
I'm Corey Colbert.
And I'm Mark Fabros.
We're a group of 4 undergraduate chemical engineers who have been assigned to a project to design and construct a safety relief valve laboratory for the UA Department of Chemical and Environmental Engineering. Before we get started, I'm going to talk a bit about the concept of overpressurization and what causes it. Overpressurization occurs when the transient air pressure exceeds the atmospheric pressure. Several factors that lead to overpressurizations are excessive rise in temperature, uncontrolled flow, loss of containment, and incorrect mixing. Our system will have to undergo overpressurization while maintaining overall laboratory safety. The purpose for that is to allow the undergraduate students to use their critical thinking and engineering skills to select the most suitable safety relief valve and vent line for the process. Let's walk you through our design. Our lab consists of an air compressor followed by a medium 60-gallon pressure storage tank and a smaller 30-gallon testing vessel. Compressed air will leave the compressor and pass through a regulator to enter the medium storage tank at 125 psi, while in stream 8, the compressed air will be regulated to enter the smaller test vessel at 75 psi. The air leaving the medium pressure storage tank will either travel through stream 4 or 6. Stream 4 will enter a pop-up valve where it has the property of allowing a quick release of air into the testing vessel. On the other hand, Stream 6 will enter a metering valve, followed by a ball valve, where it allows a continuous flow of air into the smaller test vessel. The pop-up and ball valve have an electric actuator attached to them that can be controlled through LabVIEW. A back pressure control regulator is placed on the drain pipe in Stream 9 to maintain the pressure under normal conditions. In Stream 11, the air enters a safety relief valve that discharges into a T-valve, where the student gets to test which vent line should release the air. The system will cause overpressurization that will cause a safety relief valve chosen by the students to release the excess pressure. 6 safety relief valves will be issued, in which 5 will be resettable and 1 will be non-resettable. Resettable valves have the characteristics of being easy to set and reset, whereas the non-resettable valves require resetting by hand and have a disadvantage of having a one-time use. 2 thermocouples are added to measure the temperatures. That will allow the students to use the equation PV equals nRT to figure out the flow rates. The students will determine the type of safety relief valve and vent size based on the time of discharge, the cost of the safety relief valves, and how it affects the discharge rate.
A few calculations were conducted to determine the correct sizing required. In order to calculate the area of discharge for the system, we used the API 520 method. Using this method, we calculated several areas needed to reach 20% of the set pressure within 30 seconds to 1 second. It was discovered that the area required for the shortest time was 0.00231 inches squared. This is a whole order of magnitude smaller than any commercially available safety release valves. Moving on to our P&ID, the bottom sections was all finalized and the fittings were ready to order. The price for the bottom section was calculated to be $2,438.28. The prices for the top section of the design is put on hold to conduct further research on the size of safety relief valves to match our specifications with the calculations conducted previously.
Unfortunately, due to COVID-19, our research for appropriate safety relief valves and build portion of our project was cancelled. To overcome these setbacks, we came up with alternatives that will help us move forward in our project. Instead of programming the valves on LabVIEW, we programmed the LED to indicate when the valves are switched on and off. To make up for testing our design and collecting our results, we shifted into a theoretical project named T2 Explosions, which will be described later on. For now, we will present a mini video to show the work done on LabVIEW.
The time for operating the LED lights can be manipulated as desired. For a brief presentation, the first LED is programmed to switch on for 6 seconds, and the second LED is programmed to switch on for 4 seconds.
After reviewing the T2 explosion, the chemical safety and hazard investigation concluded that the cause of the incident was due to improper sizing of the safety relief valve and a failure to the cooling system. It was also noted that the cooling system was using city water, which may lead to fouling. We decided to continue on with the project and determine how the CSB decided that the pressure relief valve should have been set to 75 psig rather than 400 psig. When considering the explosion that occurred at T2 Lab, we primarily focused on the first exothermic reaction that occurred. Because if the cooling system had succeeded, the second exothermic reaction would not have happened. To determine proper design of the cooling system, the amount of energy it was giving off, at minimum, had to equal the amount of energy being generated by the batch reactor. We took into consideration the chemical reaction occurring in the system, and used knowledge from chemical reaction engineering to solve this problem. We used this equation: the heat generated equals the heat of reaction times the reaction rate times the volume, as our basis of solving for the heat being generated. The heat of reaction and volume are both values gathered from our resources, and the reaction rate was calculated. The reaction occurring is a first-order elementary reaction, and reaction rate constant was another value from our resources, while concentrations of A and concentration of B were solved from the information given in the article. The article we use lists the initial amounts of MCPD and diglymine used in the reaction. By dividing those values from the volume of the reactor, we were able to calculate the concentration at the end of the reaction. To calculation, the heat removed, this equation, heat removed equals mass times specific heat times temperature minus the initial temperature times 1 minus the exponential of the overall heat transfer coefficient divided by mass times specific heat was used. After conducting our calculations, the value of heat generated is 2.6 times 10 to the 4th watts. So in order to cool the batch reactor, the cooling system would need to give off energy equal to or greater than that amount.
Possible alternatives are to upscale the experiment, or further research for smaller scale safety relief valve is required to enable the design to become applicable. LabVIEW should be programmed to randomly switch the actuated valves on and off. In T2 explosion, rupture disk should be set at 75 psig to prevent further pressure increase. Implement a demineralizer or avoid evaporating the cooling water inside the jacket. The required heat removal is 26,000 watts or greater.
We'd like to thank the UA Department of Chemical and Environmental Engineering and our mentor, Dr. Ogden, for all their help and support. Thank you for watching.